Yeah, hello everybody. Welcome back to the lecture on Polymer Science and Processing. In the second part of the lecture, we will focus on polymer synthesis, and I will introduce to you a technique that is known as step growth polymerization. So we can directly jump into the lecture. What we want to learn about is how we can actually, what the principle behind the step growth polymerization is. Then we will look at different synthetic approaches along with technologically important examples, and then we will do a short theoretical treatment on how we can describe the step growth polymerization and especially predict the degree of polymerization. And finally, I will show you a little trick on how we can circumvent some problems that can arise with this technique, for example, in interfacial polymerization. Okay, so let's directly start with the formation of polymers via step growth. And let me just start by asking a very simple question. How can we actually make polymers? And this brings up or takes up an introduction that I gave you last week in the introduction. What we need to do is chemistry. So what we do is we start with monomers, and then we induce a reaction that links one monomer to the next. So now the question is, how can we generally do this? And there's two approaches. One takes this reaction step by step, hence step growth. This is what we will look into in detail today. And the other type of reaction is a chain growth polymerization, where we start with one active species and that very quickly propagates and adds one monomer after another to instantly form a long chain. Okay, but today we want to do or take the slow approach if you want and devise a chemical reaction that really adds a monomer one step at a time. And very simplistically speaking is, we have a monomer that has a functional group A and a second monomer that has a functional group B. And now we ensure that each of these monomers has two of these groups. And we also ensure that A can only react with B. And if we can do this, then in the course of time, more and more reactions will take place. And this will lead to the formation of longer and longer polymer chains that always alternate between AA and BB monomer. Well, and what we of course can also do, we make our life a little bit simpler, we devise a monomer that has one A and one B group. Now A reacts with B, and then you always kind of link them together in that way, and you form a polymer that goes AB, AB, AB. Okay? We call this a step growth because literally it grows step by subsequent chemical reactions. So if we do this, then we instantly create polymers that have certain characteristics. The first and maybe most important characteristic is that the functional groups will always be in the polymer backbone. And the reason for this is very simple, because we take advantage of a reaction between the functional groups to actually make the polymer. So in a sense, the functional group is always the linker between the monomers in the backbone. And this is a very fundamental difference to a chain growth polymerization that you will see 2 lectures in the future. Okay, we see that the functional groups come from the linkage, and we can also directly keep in mind that these functional groups in the backbone also determine the properties of the polymer. So if we have functional groups that, for example, interact with each other, for example by hydrogen bonding, then we can directly anticipate that such polymers will have strong attractions towards each other and make a much stronger material, because it will take more energy to separate chains from each other. And this is the reason why a lot of high-performance polymer materials are synthesized by step growth, because that very nature of the polymerization is exploited in the application. Okay, so what kind of chemistry can we use, or what kind of functional groups can we find in the backbone? So here is a probably non-exhaustive list of such potential groups that we have in the backbone. And you see that very typical polymer classes are included here. We have polyesters that have these ester functionalities. We have polyamides that have these amide functionalities, polycarbonates, polyurethanes, and so on and so forth. So you see each of them, or you can already picture each of them, has been synthesized by merging 2 mutually reactive functional groups, and we will now go through this, if you want, overview step by step, and I will introduce you the different reactions that lead to the formation of polyesters, polyamides, polyurethanes, and so on. So this will lead us to the synthetic approaches and directly give technologically important examples. We will start with polyesters. Now take a minute, or maybe a second, and think about what kind of polymer products you know, or what kind of materials you know that are made from polyesters. Now again, I invite you to look through your room, or maybe see what you're currently wearing or what is on your desk, and then think about what of these materials you know is made from polyester. Well, there's two very important or very characteristic materials. One is PET bottles. That's something we already referred to last week, polyethylene terephthalate. And these bottles, this is the typical material for materials that contain especially carbonaceous water, soda, and so on. Not typical PET bottles. And the other very typical substance class or class are fibers. So you have flexibility in clothing, which the polyester can do, but yet it's in a fiber form, it's fairly strong, and it doesn't really tear apart too easily. So your typical running tracksuit or clothes are very often contain polyesters. So how do we do polyesters? What's the chemistry of polyesters? So in order to form a polyester, we need an alcohol to react with a carbonic acid. Of a diol. So how does this look like? We have our diol here, and we let it react with a molecule that contains two organic acids. So in this very generic reaction scheme. And now we need to see why these materials react. And I know this is a lecture that is part of an engineering colloquium. So for those of you that have a good understanding of organic chemistry, the following steps may be very trivial and very easy. I will still repeat the chemistry in its details so that everybody can really follow and understand how and especially why these molecules can react. So first of all, let's identify reactive centers in these molecules. Start with the diacid, and in the diacid, a very reactive center, or the reactive center here, is the central carbon atom. And why is that? Oxygen is more electronegative compared to carbon. We have this carbonyl bond, this oxygen has 2 free electron pairs, that pulls the electrons away from the carbon. So you have a partial positive charge or a deficit of electrons at this carbon. So this means this region here is susceptible to an attack by something that has a lot of electrons. Or it can react to something that has a lot of electrons. And now we just need to identify a material that has a lot of electrons, which we call a nucleophile. And we see here that the oxygen of this reaction actually acts as a nucleophile. So here, this is partially negatively charged and can react with this electron-lacking carbon atom. So these electrons attack here. Then we form in the first step when this reacts, it has 5 binding sites, so we need to make space at the central carbon, and if there's a carbonyl bond, like a CO double bond is involved, this will always clap out and then make space. So we have here now the electrons all at the central oxygen. We have another two and the OH group. Okay, so now obviously this is a situation that's not very sustainable because we have a positive charge at this oxygen here, and this carbonyl bond wants to recover the double bond because this is very low in energy. So in the next step, this bond reforms, and for this something has to yield. There's 2 options, either this can yield and then we go back in the other direction, so this is an equilibrium reaction, or we can get rid of the OH. And if this happens, then the OH can get out, and while it goes out, let's put it the other way around, it can directly take the hydrogen with it, and this makes up space at this oxygen center here, and then we have the formation of an ester. So here we already see the typical functional group that we know as an ester. And we free up water. Okay, so this is very basic organic chemistry, and of course then this reaction can go on and on if more and more of the functional groups react, and eventually we form a molecule with a repeat unit that will look like O. Now we just need to see where we need to set our brackets. So N, and then we get also we release water. So we see now when I add these packets here, what this indicates is that while I propagate along the polymer chain, if I go out here, I re-enter here. And you very clearly see the 2 components, the alcohol and the acid that are joined via this carbon bond. So now since this is an equilibrium reaction, we need to do something to push the reaction into onto the side of the polymer. And very clearly, if we release water, then what we can do is simply heat up or remove water by any other means. So if we increase the temperature here, water will evaporate and we can drive the equilibrium to the side of the product. And this is how we can form polyesters. Now we can make our life a bit easier. If we don't want to use high temperatures, we can use a different starting material that reacts a bit easier with alcohols, and that is the reaction of a diacid halide with a dialcohol. And in this case, the reaction looks very similar. So we still have our alcohol here, or dialcohol. Now we don't let it react with a carboxylic acid, but with an acid halide, or Säurechlorid in German, and this then will look like this. But everything else remains the same. So now this carbon here is even more deficient in electrons, because we have a very strong pull of the chloride because it's very electronegative, and we have a pull on the electrons of this oxygen group, and that means there's very little electrons here. So again, we need a savior that brings electrons. This is this one here. In order to do this, the carboxylic acid will go out, and then we have first our reaction adduct. And now the situation can resolve very quickly as well. So we need to regain our carboxylic acid. The chloride can leave. While it leaves, it can take the hydrogen. In this case, the electrons go back to the oxygen, and we form this bond. And if we do this more and more, then we get the same reaction as here, and we end up with a reaction that you actually don't really see. Oh, sorry. Now you don't really see anymore that you had this acid halide, except for here this end group. So you see, and you need to remove HCl. So very simple chemistry, and what we do is, as we said, literally link one molecule after the other. Here you see this again in black and white. And the second reaction, because we release HCl, which is a gas, we can conduct at room temperature. Okay, let's go to the second polymer class that is fairly important. And this is polyamides that are much more typically known as nylon. So again, my question to all of you, what materials do you know that are made from nylon? Or what products? No, the material is nylon. What I can think about, look around your room, maybe your cellar or so. Well, there's a lot of materials made from nylon. One fairly important one is outdoor equipment, or let's say fibers very generally. And this can have any kind of properties from stockings, fairly stretchable soft materials, to climbing ropes that are fairly durable, because you don't want the material to break when you fall down, but also a little bit flexible, so it needs to give way a little bit, otherwise you break your neck when you fall down. Or, for example, the material of tents, which also needs to be very lightweight, because you need to carry it around, but it also should be sturdy, so it doesn't tear when there's a storm coming out. And sturdy is something that nylon can do fairly well. Other materials that are made from nylon type of materials are really high performance materials. Bulletproof vests, and we will talk about this in a second, are also made from nylon, or these durable protective gloves that you can use whatever to lift off glass, or even to take coals out of a fire when it's really hot, and so on. Protective clothing, flame-proof fabrics are also often from aromatic polyamides. So a lot of things to wear, typically in more of the high-performance applications. And by the way, I mentioned this last week already, stockings, the same material that is now used in stockings, was traditionally used in parachutes. beforehand. No, this is what it was invented for. Then there was no need for parachutes anymore. So the industry had to come up with a different solution or a different product, and then they developed stockings. Okay, so how do we do nylon? Let's briefly look at the chemistry of nylon. So nylon or polyamides are formed by a reaction with an amino functionality and a carboxylic acid, or maybe a carboxylic acid halide. And of course needs to be dicarboxylic acids. So how does this look like? We have our diamine. Amino groups always have an electron lone pair, and we have a carboxylic acid. And now for the sake of simplicity, let me draw it like this. So this is the central carbon, R2. Now again, if you look at the reactive centers, nothing has changed from the side of the carboxylic acid. Still, this here lacks electrons because they are more polarized towards the oxygen. And now it's looking for a reaction partner that has a lot of electrons, so a nucleophile. And you see the amine, anything I said for the alcohol is especially true for the amine because it has this very pronounced electron lone pair here. It's electronegative and pulls all the electrons of the hydrogen to it. So this definitely has a partially negative charge. And that means that it can, this lone pair can attack here. Again, this bond yields to make space. And in the first reaction step, we get our reaction adduct. This is negatively charged, and this nitrogen here just lost its electron lone pair because this is now in the bond, so it has a positive charge. Now again, a positive charge on an electronegative element is never very stable, so we need to try to see how we can relax the situation. Again, this carbonyl bond wants to reform to reduce the energy, and again there's two options. Either we kick out the amine again, which we can do, of course, but then the reaction will go in the other way, or we can kick out the bond to the OH group. This can take over the hydrogen, and when it does so, the amine recovers its electron lone pair. And now what we have formed in this step is an amide bond. And now, of course, you can, as before, and of course, what we also have here is a water molecule. So now we can force the reaction more and more to propagate in this direction. And when we do this, we get more and more bonds that are being formed. And then again, we form a longer and longer chain. I just need to write this out here. And now we need to see where to make the brackets. And here we have a long polymer chain. It means we go through here, we discover our initial amine, we discover our initial acrylic acid, carboxylic acid, and if we enter here, we arrive at the next amide bond. So this entire polymer is now linked together by these amide bonds. And if we want to force the reaction to go into this direction, we need to increase the temperature so that we can evaporate the water, or remove the water by other means, can distill it away to drive the system into to the product side. So then we can, of course, play the same trick if we want to have something more reactive. Now I just want to speed up a little bit. We can replace this OH by an acid halide. If we do this, the center becomes even more reactive. Anything else remains the same. Now we have a chloride here. This chloride will then leave, and not as H2O, but as HCl, by taking over this thing. And then, of course, we would have HCl formation here as well. Anything else remains the same. Okay, and just for the sake of completeness, what we can also do is a self-condensation of a material that we before called AB monomer, so that contains both of these functionalities. In this case, it would be a molecule that has an amino function and an acid function, and that's why we call them amino and how this will look like is very clear. We have H2N now this amine can directly attack here or on a different material. That means we create this bond here, and at the end of the day we create a polymer that looks like this. C, R, and maybe this looks familiar to you, these type of structures. This is exactly what we find in proteins. Or, if they're a bit shorter, peptides. Good. Let's have a quick look why nylon is such a stable and sturdy material. So very clearly, if you make a climbing rope, then you do not want to have the rope tear easily. Also, nylon as kind of the yarn is very stable. And the question, why is that? Of course, a bulletproof vest will be the ultimate example of such a stability. So what you need to introduce are groups that provide attractive interactions between neighboring polymer chains. And now we can directly see, if we, for example, take this polymer here, why nylon is so effective, or polyamides are so effective in doing this. Now you can see we always have an NH in the neighborhood of a C double bond O, and both of these groups can undergo hydrogen bonding with each other. So every time we have this in the vicinity, we can have the next polymer. Hydrogen bonding. Okay, but we need to draw it the other way around. So here and here again, we can have a hydrogen bond to this one. So each of these units can form two hydrogen bonds with neighboring polymer chains. And of course, it's not only one bond per chain, but throughout the entire chain, you can create these hydrogen bonds. And this makes it very stable. Let me show this to you in the blackboard, and it becomes even easier visible. So here again is the chemistry of nylon. Maybe one word to the nomenclature. Very often you read something like nylon 6,6, nylon 6,10, nylon 6. These numbers simply denote the numbers of carbons in the amino group or in the amino molecule and in the carboxylic acid molecule. So as an example, nylon 6,10 is made from an amine that has a C6 chain in between and an acid chloride that contains 10 carbon atoms. 8 in the chain, 9 and 10. And this is why it's called nylon 6,10. So you count the carbons. Okay, so here's an example of something that is very sturdy. This material is known as Kevlar, and this is, for example, what is used in bulletproof vests, in fire-resistant materials, what the firefighters wear. When you have torches, the material that soaks up the oil to light the torch is also made from Kevlar. So you react an aromatic amine with an aromatic diacid halide and then create a nylon type material or a polyamide that is only composed of benzene rings and amide bonds. These can undergo hydrogen bonding, and these are very rigid and stiff materials. And because they are so stiff, there is no flexibility in the chain. So the flexibility or the dimensions of the chain are always the same. And that means that when you form one hydrogen bond to a neighboring chain, you automatically align the next group, because this cannot move around too much. In an aliphatic chain, like in nylon stockings, there is much more flexibility because this aliphatic CH chain can move and can twist and rotate, and that means that not all hydrogen bonds are aligned. If you have an aromatic unit, you always fix the distance, you fix the orientation, and that makes it very easy, like in a zipper, to form a complete set of hydrogen bonds. So again, you see this here, you always hydrogen bond to this polymer chain, there's one more here and here and here. So with each repeat unit, you generate two hydrogen bonds to neighboring polymer chains, and very accurately in the case of these aromatic polyamides. And this is why, for example, you use them in bulletproof vests. Now it's very hard to remove them. And you see that apparently the interaction is so strong that it can literally catch a bullet for you. Okay, here's an article that I found a few years ago in The Economist. Pump it up, Scotty. The International Space Station gets an expansion module. This is the expansion module here. So in a sense, there is a new tent at the space station. If you're interested, you can read the entire article. It's called the Bigelow Expandable Activity Module, or catchily abbreviated BEAM. And now, blah, blah, blah. BEAM is made from cloth. It's folded up and stowed in the journey into orbit, much like a tent, and then inflated to its full size. So this is exactly what you want to have as a tent as well, something that is very handy and lightweight and easy to carry around, especially if you want to shoot it in a rocket to the space station. Yet, of course, compared to your average tent, it needs to endure much more hostile conditions. Now, first of all, it's very cold, but secondly, there's a lot of stuff lying around, and this flies around very, very fast. If it hits your module, you by all means want to avoid that a hole is poked into your tent, because otherwise, of course, because of the vacuum in space, all the air will be sucked out and will be very detrimental. So really, this cannot be a classical tent, but what this is made from is, as we see here, at the same time, the module's thick fabric walls made of tough layers of exotic materials such as Vectran, a Kevlar-like substance used in rope making, or Nomex, which is used to make firefighting clothing or to offer the astronauts better protection from the hazards of space than metal walls do. So people at NASA or ESA or whoever was in charge of this module apparently preferred this polymeric material And Kevlar, as I said, is this aromatic polyamide I showed you before, to metal. Now this can show you how durable polymeric materials can actually be. Okay, moving on to the next substance class, polycarbonates. So anybody now can already start to guess what a polycarbonate is, and meanwhile I'm cleaning up the blackboard. So polycarbonates, what do we use them for? You find them, for example, as the back cover of DVDs or CDs. You find them on the windshield of cars, or in some cars, especially more expensive cars, as the shield of motorcycle helmets or in greenhouses and so on. So it's a very transparent material that still is fairly strong, and transparent. So shatterproof glass, DVDs, and so on are made from polycarbonates. So now the question is, how do you make polycarbonates? And polycarbonates, maybe I can just show this here on the screen. The carbonate function looks like this. So you need to, let's switch it off. So you need to find a substance that can kind of attack the central carbon twice. We've already seen how we can make this one. Now this is our ester unit. So clearly the reaction of an alcohol with a carboxylic acid or a carboxylic acid chloride creates an ester. And now you need to do the same thing twice. Now it's up to you to tell me what kind of a carbon substance or acid substance I need to use in order to reach this, if you want, double esterification. Okay, think about this a little bit. So we need to let react a dialcohol and we need to let this react with the missing substance, and this, what is used, is typically a substance that looks like this would make the first ester, and then we need to create a second ester. And now we do exactly the same chemistry as before. Now this attacks, this group goes out, this will be kicked out, and then we do exactly the same thing on the other side as well. And then what we end up having is a polymer and let's see where the repeat units are. Like this. Okay, so hang on, and what I'm missing here. This is the carbonate function, and this course extends all over the polymer. So how this looks like in real life, you can see here. Very often they use bisphenols, which is this material here, and this substance here is called phosgene, and this creates this polycarbonate. Okay, and you release HCl. Now the question is, why is that a very dangerous reaction? And why is it not something that a lot of people want to do in their chemistry labs? Well, for starters, bisphenol A looks a little bit like a hormone, so this is kind of under suspicion to interfere with your metabolism and with your body. So it's not something that you want to use generally. And this reagent here, phosgene, is extremely reactive. No, it has twice this acid halide functionality, and it's a gas, if you inhale this, you directly hydrolyze the substance, so you create HCl, or you release HCl in your lungs, and then you pretty much directly die. So this has been developed in the First World War as a toxic gas, as a poisonous gas for chemical warfare. And this, of course, is not something that's very easy to handle, and especially not in your average chemistry lab. So this is really the problem about this reaction, that it contains very potentially dangerous substances, and you need to be careful about it. But yet, of course, if you do this industrially, this is something you can get under control, and then you can make very important materials because they're transparent and they're very shatterproof and stable. And again, because of the possibility to interact via polar interactions. So what can you do with it? We already talked about where we find this, and this used to be used in baby bottles as well. This type of reaction, of course, is not anymore. And now, if there's chances that one of you will have a drinking bottle made from plastic on his or her desk, and it may say BPA free. So, for example, these Nalgene bottles that are very popular at the moment, they always have this label saying that it doesn't contain PBA, and BPA is bisphenol A. So there's exactly a polycarbonate chemistry involved, but they got rid of this type of chemistry. But yet, if you have this, you can give it a try. You can pretty much throw this down a rock and it will never break. So they're really very sturdy and very shatterproof. And this is why you want to use this in any application where you require high mechanical stability, like in a windshield of a motorcycle helmet or so. Good. Okay. Here you already see the concerns. The next class, polyurethanes. And this is probably the most widespread polymer class that exists. So it's very versatile. And examples on where we find polyurethanes range from clothing, especially spandex, so your Speedos are made from polyurethane, to coatings, so any coatings in the automotive industry. If you paint your garden furniture, for example, this is all polycarbonate-based polymeric materials, but also all kinds of foams, ranging from very simple dishwasher foams to insulation in construction materials, so construction foams. These are all made from polycarbonates, from polyurethanes. And again, of course, this brings up this interesting question, how we can control the properties from the princess on the P and the helmet of Evil Knievel or the stunt woman, that one needs to be very hard and protective, and the other one needs to be, if you want, very soft and gentle. Now let's see what we can do and how we can influence these properties. So to start with, we need to understand what a polyurethane is and how it forms. So polyurethanes form by a reaction with a diisocyanate with a diol. Now, diols we have encountered multiple times already. Now the question is, what is a diisocyanate? And that's probably not something that everybody knows. A cyanate function looks like this. So this is the diisocyanate, and it consists of this very peculiar group that has a carbonyl bond directly coupled to an NC double bond. And we can let this react. With the dialcohol. Now again, let's have a look at the chemistry or at the electron densities involved. We already suspect why we need a dialcohol. Similar to before, this is nucleophilic because it has these 3 electron pairs and a lot of electron density at the oxygen. So what is going on with this weird molecule here? So we first realized that again we have a carbonyl functionality, so we will suspect that probably a reaction will occur where this one will open up. And we already know that this central carbon here is electropositive. Now here it's especially electropositive because this nitrogen here also pulls on the electrons. So here again it's in between 2 partners that pull electrons away from the carbon, so this really yearns for more electron density. And here comes the solution. This will first attack, and now again something needs to make way. So we can form. Now I just abbreviate this whole thing a little bit. So very similar to before in the case of polyamides or polyesters, we get this adduct. And now, of course, this nitrogen has a free electron pair here. So the carbonyl bond wants to recover. This oxygen is not very happy because it has a positive charge and would rather get its electrons back. And luckily, the nitrogen can jump in here, take over the hydrogen. So this means that this oxygen gets the electrons back. Now the nitrogen is lacking electrons itself and opens this bond, which is necessary anyways because we form a double bond here and we only have 4 binding sites available. So after all this juggling of electrons, what we end up with is the rest of the molecule. This nitrogen now has a lone pair and a hydrogen. Then we have a single bond here to the carbon, a double bond, and this here, this bond type is called a urethane bond. So again, a bit similar to a mixture of an polyamide or an amide bond and an ester bond, just in one single molecule. Okay, now interesting, and compared to polyesters and polyamides, we do not release anything from the molecules here. So there's no water being released, and this is why this reaction is known as or called a polyaddition, as opposed to a polycondensation, where you condense 2 molecules and release water. Okay, this makes it easier for this reaction to occur because you don't need to bring the equilibrium in a certain direction. Either it's energetically more stable, then it will follow the reaction path, or not. Okay, so this is how we can form polyurethanes. And now the next question is, how can we now control whether we make a mattress or a helmet? And again, we already see that this polymer can be fairly strong because we have the possibility to hydrogen bond here and hydrogen bond here. So this makes it inherently mechanically robust because there can be interactions with the neighboring chains. Now, how do we change the properties if the structure of the bond is already given? There remains only 2 possibilities. We can change R1 and we can change R2. Okay, and now depending on what we choose as these organic functionalities, we can make it stronger or stiffer and more rigid, if we, for example, choose aromatic units, or we can make it more flexible and more stretchable if we choose long-chain acrylic materials. Okay, and this is exactly how these things are controlled. So the bicycle helmet will be much more stiff because one of these, or at least one of these, will be an aromatic unit, and spandex or clothing that are very stretchable are made of aliphatic molecules. Okay, but we also need to continue the reaction here. Of course, this is only the first bond. I mean, the rest is somewhat trivial, so we go into a material that then has one bond left. Now we're here at R1. Now we form our urethane bond. R2, O, R2, and then R1, O, and so on. And then here it will continue in H, R2, O, and so on. R1, C, and so on. So the repetition unit will start, let's say here, and then we have our polyurethane, this O, R1, so we enter here. Okay, so this is how we make polyurethanes. Now the next question that imposes itself is, how does the foam get into the material? Okay, and this is also hidden in the chemistry of polyurethanes. And what we see is, let me just write this down again. So we have a polymer or a monomer that contains this isocyanide group. Of the polymer, and now we don't let it react with a dialcohol, but with water. And chemically speaking, water is, if you want, also a type of alcohol. No, it also contains an OH group and a second OH group, so it's structurally very similar. And of course, it will undergo the same reaction here, and that is that this attacks here, this opens up, so we create at the end of our polymer this intermediate state. Now this proceeds as in the normal urethane bond formation. This opens up, this nitrogen bond goes here, the lone pair takes over the hydrogen, and this recovers its electrons. So that means we have a situation that looks like this. And now, let me draw it a little bit differently. Now we see this is where the normal reaction stops. But here, this molecule has another way to relax a little bit more and reduce its energy a little bit more. So what we see is that we have the possibility maybe clearer like this, to actually form another double bond here. If we do this, then you see that we have a structure of CO2. But for this bond needs to give way. That means the nitrogen needs to react with something else, otherwise it has too many electrons. and it can take over this hydrogen here so that these electrons are recovered. Okay, so with this juggle, what we get is an NH2. Now again, you see this bond pretty much goes in here, this bond goes out, and the lone pair takes up the hydrogen. And we release CO2, which of course evaporates because it's a gas and drives the reaction. And especially if this gas is released in the course of the reaction, it foams up the whole material, no? Because you have a gas source straight in your material. And this is how you create these polyurethane foams. So either you add water on purpose, but very typically you don't need to do this because there's enough water in humidity, and then it automatically starts to foam when you spray it out of your bottle. Okay, this is the trick of the polyurethane chemistry. In your bottle, you have very small polymers so that they still remain mobile and liquid. These polymers are made in a way that they contain isocyanate groups at the outside. Then, while it sprays out, they undergo a reaction with water, start to foam, so you foam up the polymer. And now the last trick, the amine can continue to react. So let's say additional reaction, amine plus diisocyanate, or strictly speaking, it's actually not a diisocyanate anymore because it's already bound to a polymer, but this isocyanate. And this forms a urea bond. And for the sake of completeness, I just show this to you briefly. So we have our polymer that contains NH2 groups now. No, this is here the rest of the polymer. And we let it react with another polymer that still has isocyanate groups as it comes out of your foam bottle. And everything that we said before is true again here. The amino group has a lot of electrons, attacks the electron deficient carbon. This opens up, so we create in the first step this adduct, and somewhere I forgot a plus. Now, and the reaction proceeds fairly similarly. This bond reforms. The nitrogen takes over on hydrogen, takes one of these binding electrons from the C double bond N. As the hydrogen goes away, this lone pair is recovered, so the positive charge is balanced, and we receive something that looks like this. NH, CO, NH, and another polymer. And this reaction is called urea bond formation. So you see, again, to make this foam, two things are important. First, you have actually three things. You need to make a pre-polymer that contains these isocyanate groups at the outside, and you will see in a second. You do this by adding a bit of an excess of the isocyanate in the first reaction. So this comes out of the bottle, takes up water, converts into an amine and CO2, so it starts to foam up. Meanwhile, this amine continues to react with more polymer that comes out of the bottle and forms a urea bond, which hardens the material even further because the polymers become longer. And this is how you make this very stiff construction foam or insulating foam. Okay, so much for the polymer chemistry. Now we take a deep breath. I clean the blackboard. And then we look a little bit at the theoretical treatment of such reactions. So now here again is the reaction that you see. Diisocyanate, this is how it forms. It creates this urea link. Now we can shortly summarize, or maybe do this for yourself. What kind of polymer classes do we have? Which monomers do we use? What type of reaction do we have? And examples. So for those of you that are literally in my lecture, this is something we will do in the next week in the discussion session to kind of summarize that a little bit. Okay, so now let's look at the theoretical treatment of step growth polymerization. And especially what we are interested in, since this is based on organic chemistry if you want, is how many reactions do we need to perform to achieve what kind of molecular weight. So what do we need to do to make very long polymers? And this is something that already Wallace Carothers, that I told you last week, came up with a concept on how we can use very simple predictions to show how long the polymers will get. And the whole thing is based on this assumption. Now take these as monomers. Whenever they turn black, they reacted, and then we count how long the polymers get that we form. So with each reaction, we just join 2 monomers. So in the beginning, if we have a conversion of 25% of the monomers, we only have very small polymer chains. That's maybe not surprising. But now in this case here, if you count, it's 50% of the dots are converted. Still, it's not really long polymer chains. Now there's maybe 4 or 5 or so, but everything is not interconnected, simply because each molecule reacts very separately from the other one. And even at 75%, now you start to interconnect some of the chains anymore, but you still have significant amounts of unreacted materials and of very small dimers and trimers. So the conclusion from this very simple picture is that apparently we need to wait for a lot of monomers to convert into polymer before we start to see long polymer chains. Okay, and this simplified picture is something we can also relatively easily put into numbers, and this is something that we want to do now. And this is a formalism that has been invented by Wallace Carothers. Hence, it's called the Carothers equation. So what do? We first start with a very simple system. And we let an A, B monomer react to form a polymer of interconnected A, B units that have a certain chain length. And what we want to know is how many reactions do we need to do to get what kind of a chain length or what kind of a molecular weight. Okay, so now let's make a couple of definitions that we will also need for the next, maybe a bit more complicated step. So N0 is the number of molecules at the beginning, before the reaction started or at the start of the reaction. And capital N subscript T are the molecules, and in this case this can already be polymers, so the total amount of molecules at a certain time T equals T. Okay, and then something that we do not need right now, but what we will need a little bit later, Na and Nb will be the numbers of functional groups A and B. Why don't we need this right now? Well, it's fairly simple to see. If we use such monomers, the numbers of monomers at the beginning is exactly the same as the numbers of functional groups A and B. So Na equals Nb equals N0. So it doesn't really matter. And now the last thing that we need to think about is how we can describe xn. And xn is the degree of polymerization, so how long the polymer chains are. So the average chain length in our material. So the first thing is we need to think about how we can express xn in terms of these numbers that we have here. And a very simple way to do this, and this is what this Carothers equation is based on, simply states that, let's put it here, xn is the numbers of molecules that were there at the beginning divided by the numbers of molecules that is there at the end of the reaction or at a certain time t. So what kind of assumption is this? I mean, we can make a very simple sanity check. In the beginning, we would expect that we don't have a polymer. And in the beginning, Nt would equal N0. So the average degree of polymerization would be 1, which means no polymer formed. That's okay. And let's say we are very good chemists and we drive our reaction to the perfection. That means that all monomers have been converted to one single long polymer chain. And if this is the case, then Nt equals 1. And if Nt equals 1, then Xn, so the degree of polymerization, will equal N0. That means the polymer is exactly as long as the total numbers of monomers that we put in. So this makes total sense. And anything in between, of course, will be somewhat in between these two extrema. So as you see, it's a very simple way to express what we would expect as an average molecular weight. Okay, so now let's continue. So now we look at the conversion of monomers. The monomer conversion, and this is typically called small p, and this is defined as the number of reacted groups divided by the total number of groups at the beginning. Okay, this also makes sense. Of course, a conversion means that a functional group is converted into a polymer structure, and therefore if you want loss to the reaction, so that means the more of groups you react, the higher your conversion, and then of course you normalize against the initial group, so it runs from 0 to 1. 0 is no conversion, 1 is full conversion. Okay, in our case now it's very simple. Here we talk about groups because what is reacting are the functional groups. No, strictly speaking, not the molecules themselves. In our case, it doesn't matter because each molecule has exactly one functional group A and one functional group B. So what we can now express P with is N0 minus Nt. So per reaction, we lose one functional group. So in the beginning, we have N0 functional groups. At a certain time t, we have Nt groups. So the difference between them is the numbers of groups that have reacted. And the initial groups, in our simple case, as we said, equals N0. So now that means that P equals N0 divided by N0 minus Nt over N0, and this is 1, and Nt over N0, if you look here, is 1 over Xn. So this means 1 and this is P. And now you need to invert the entire thing, and then what you find is that Xn equals 1 over 1 minus P. So now we have found a very simple functional relation that connects the conversion P with the expected chain length that we have in our polymer. And now we can maybe make a very little drawing here. Conversion P over xn. And now we pick a couple of numbers. So we can start with 0.5. 50% of the group have reacted. What we will get is P is 0.5. 1 minus 0.5 is 0.5. 1 divided by 0.5 is 2. So then we can maybe pick an example of 90% conversion. So in this case, P is 0.9. 1 minus 0.9 is 0.1. 1 divided by 0.1 is 10. And if you pick something in between, then whatever, let's pick maybe 0.7. 1 minus 0.7 is 0.3. 1 divided by 0.3 is approximately 3. So if we're here, then we're approximately maybe here. And then if we go to 99% conversion, P would be 0.99. So this would make the denominator here 0.01. And 1 divided by 0.01 is 100. So then suddenly it ramps up very quickly. So we see that the functional relation is something that looks like this. So indeed, you need very high conversions to create very good polymers or polymers with a very high molecular weight. That's the first very important take-home message. We need a very high conversion in order to get good polymers. And this is, of course, if we want bad news for polymer science, because high conversion means you need to make very accurate reactions, you need to be careful, you need to wait for a long time, you need to make sure that everything reacts perfectly. So this is pretty cumbersome. And we will see in a few lectures there's other types of polymerizations that do not have this requirement, which makes it easier to conduct them. But then again, here we have the advantage that we have functional groups in the backbone, which is a pretty good advantage to create high-performance polymers. So for some performance, you need to take this kind of into consideration, or you need to take the burden of making good reactions. Now let's make it slightly more complex. The next question we want to ask is, how sensitive is the reaction to changes in stoichiometry? So the next is, here is easy, everything is in stoichiometry. Na equals Nb. So let's see if we have a stoichiometric imbalance. And what we consider is the following reaction. We let an AA monomer react with a BB. And this, of course, then will form a polymer composed of the two materials. Okay, but now we say that there's not the equal amount of A and B. And we describe this by small r, and this will be the numbers of groups A divided by the numbers of group B. And that also means that Na equals R times NB. And we choose our A's and B's so that R is smaller than 1. So that means the species that is in excess will be species B. Which also means that the conversion we are talking about, and which we will need in a second, will be the conversion of A. Because even if all A molecules react, there will be B molecules over, or B functional groups over, because we have too many of them. And if we want to have our conversion run from 0 to 1, we need to use the minority component here. Okay, so now what else do we need? N0, the numbers of molecules in the beginning. We can now express from the functional groups total numbers of A's, total numbers of B's, divided by 2, because each molecule has 2 functional groups. And since we can express Na by Nb, we can also express it here. So this will be Nb times 1 plus R divided by 2. Okay, what else do we need? Nt, those are the 2 things we need to calculate our degree of polymerization. No, N0 divided by Nt. And this will be the total amount of groups that still have not reacted. So this is what, so the total numbers of groups that have reacted divided by 2, because it should be a molecule. So Na at a certain time t plus Nb at a certain time t divided by 2. So the numbers of groups we have left at a certain time t plus the numbers of groups B that we have left at a certain time t divided by 2 will give us the molecules we have left at a certain time t. Okay, so now we need to try to find expressions for these numbers of groups that we have at a certain time t. And this is what we will do here. Start with the numbers of functional groups A at a certain time t. Okay, so this is first fairly simple. We look at the numbers of groups A that we had at the beginning. And then we subtract all the groups that have reacted. P is the degree of conversion of groups A times Na. This gives us the total number of groups that have reacted. So this is also Na of 0, not the functional groups that were there and the ones that have reacted. And now we can also express everything in terms of Nb. And you will see in a second why I do this. So this will be R Nb minus P R Nb, or simply R Nb times 1 minus P. Okay, next we look at the functional groups B at a certain time t, the ones that have not been reacted, no, the ones that are still there at time t. So this will be the number of functional groups B in the beginning. And again, we subtract all the groups that have reacted. So the conversion is P. This is the numbers of groups that have reacted. But now, since B always reacts with an A, and this P is the conversion of A molecules, we need to be careful and write P and A here. No, because the conversion is defined as the conversion of A, but it doesn't matter because A can only react with B, so this will also be the numbers of groups B that are lost. Okay, and again, we now express everything in terms of B. This doesn't change. And B, and I just omit the zeros here to have less to write, minus P R Nb, and this would be Nb times 1 minus R P. So now we are almost done. Here's already the expression we are looking for, Nt. So Nt is an A at a certain time t plus Nb at a certain time t divided by 2. So now we can put this in here. So this would be R Nb times 1 minus P plus NB times 1 minus RP divided by 2. And now we can make this expression a little bit easier. We can take the whole product. So we have NB times R minus RP plus NB times 1 minus RP. So this will be NB times 1. This is this one here, plus R, this is this one here, and then minus 2 times RP. So from this expression and from this expression here. And again divided by 2. And now we are done. We can now express our degree of polymerization, so how long the polymers will get, again as the fraction of N0 over Nt. And if we do so, N0 we have here, so this is Nb half times 1 plus R, and we divide it by Nt, which is Nb over 2 times 1 plus R minus 2 RP, and this is the following expression. So now this gives us the expected degree of polymerization, or the expected chain length, as a function of R and as a function of P. And now again, let's make a quick sanity check. If R equals 1, we should recover the normal Carothers equation. Look at this. 1 plus R, this would be 2, divided by 1 plus R, 2 minus 2 RP. And this R is again 1, so minus 2p, so we can get 2 out of the equation, and we recover 1 divided by 1 minus p. So indeed, this expression holds for the similar case. And now we can also look at how the reaction will proceed if we change R, or vary R, from perfect stoichiometry to less and less perfect conditions. And this is something we can easier do on the slides. So again, here you have all these things. This was the Carothers equation for perfect stoichiometry. This is already what we had on the blackboard, so you see it ramps up really quickly. Okay, that's we already covered. And now here's the thing that we just did. Now we see this. Now let's look at the numbers. Here, this is the degree of conversion. So we already see for perfect stoichiometry, this goes up really, really quickly. And infinity here simply means all monomers are consumed. So it's actually N0, depends on how many monomers you have. But now if R becomes a bit less perfect, let's look at, for example, this one here. This would be 1% difference between monomer A and monomer B. And suddenly, instead of having a really, really long polymer, you have a degree of polymerization of 200 here, which compares really badly, or compare 160 to 1000. And 1% is very easily the error of a lab balance or so. And let's say you are a much more sloppy person and you don't really take the scale too seriously, so you make 5% error, and suddenly, even if you have a perfect conversion, which by itself is tricky, you only get a polymer or an average chain length of 40. So in translation, you don't really make any polymers anymore. So the second lesson that is hidden here in this Carothers equation is that you need to be very careful to balance the stoichiometry. You need both high conversion and, at best, ideal stoichiometry to make good polymers by step growth polymerization. Now that's of course asking a lot, because both is not easy and it can be quite difficult to obtain these. And this is in the last part of this lecture, last few minutes, I just want to show you 2 brief tricks on how we can overcome this issue. So we need to outsmart Carothers and somewhat find a way to get a balanced stoichiometry. And there's two possibilities that we can do, or actually three. The first is very simple. We take AB monomers. There, the issue of stoichiometry is not really a problem because the one monomer serves as source for both A and B. The second is we can make a salt. Let's assume we want to make a nylon, a polyamide. So we use a diamine and a diacid. And if we dissolve them in water or in a polar liquid, then this can be protonated and you form an NH3 plus. And an acid in water always forms a proton, H plus, and a carboxylate anion, so COO minus. So this proton that is released here in water will be caught up by the amine. So you form a positively charged amine and a negatively charged acrylic acid. And then you slowly evaporate the water, and that means that eventually you start, because they electrostatically attract each other, you start to form a crystal. In a crystal, you always have the same amounts of positive as negative charges. That means you automatically, by the very definition of a crystal formation, you form a polymer that has perfect stoichiometry. Now, this is a very simple way of achieving this if you manage to get your two reaction partners into a salt, which works well for polyamides, so for nylon formation. And then you have your salt. You can either heat it up at brute force to remove water and then directly convert it, or at least you can also redissolve it, make normal polymers from it, normal monomers from it, and then remove it. But you can directly use the salt to obtain perfect stoichiometry. And the second reaction is known as the Schotten-Baumann reaction, is a reaction at an interface. So at an interface, you have a diamine that dissolves in water. Let's say this one is water soluble, while this one is soluble in an organic phase. So you separate the two reaction partners, and only when they touch at an interface will they be able to undergo a reaction. And since at the interface there's only two reaction partners that can meet, you automatically ensure perfect stoichiometry. And this is why, mediated by the interface, you can form very, very polymers and you don't need to care about the stoichiometry at all. The interface does the job for you. And this is something for the end of the lecture that my student Salvatore will show you in a quick video to see how this process works in real life. So this is what we will show you in a second. Now we move over to the lab and look at the reaction. Well, and after this, seeing this nylon formation, let's briefly summarize what we have learned. First, we can use different chemical reactions, or we need to employ organic chemistry to make step growth polymerization. And you've seen the different reactions that we discussed. Secondly, we learn that we have functional groups in the polymer backbone, and this is important to control interactions between different polymer chains, and this yields, or often yields, high performance polymers. This is why people undergo this effort to make step growth. Secondly, we've seen that we can use the Carruthers equation to get predictions over the degree of polymerization, and especially we learned that we need high conversion and good stoichiometry. And if we cannot achieve this, then we can, that's what you see here, then we can try to out-trick Carruthers by either using AB monomers or doing a salt formation process or using an interface to ensure stoichiometry. So this is, in a nutshell, how step growth polymerizations work. I thank you very much for listening and see you in the next lecture. Thank you.